This thing here is called a Van de Graaff generator, and it generates a large positive charge on this ball. The most famous thing to do with a Van de Graaff generator is to make sparks. This one makes about 2-inch sparks. So those are mini lightning bolts. There's really 2 points to this video. The first is the Van de Graaff is probably our favorite physics toy, and I want to do all the silly demos we would have done if we were in class, just so you have seen them. So we'll play around with it in these clips. I also want to talk about how the Van de Graaff's large charge, and we're going to assume that all the Van de Graaffs you see here have a positive charge, how having an object like that affects the space around it. Nothing that's brought near a Van de Graaff generator that has charges that can move is going to act normally. It might experience a force on it, and it might acquire some sort of electrical potential energy. So we have to have some sort of organized way of looking at those two things. How do things experience force near large charges? How do things acquire potential energy near large charges? There's 2 new concepts we have called electric field, which tells us about forces, and electric potential, which tells us about energies. Electric potential is sometimes called voltage. So in this video, we're going to try to briefly outline how both of those can be defined around the Van de Graaff dome. The hope is by the end of this, you'll have an idea of some of the vocabulary we use for electricity, and you'll be able to see how, just like the Earth alters the space around it and makes masses fall towards it, charges alter the space around them and affect other charges. But before we get there, let's do a couple silly tricks. We'll provide resources for people who are curious about how the Van de Graaff generator works. But everyone should know that at the heart of it are 2 materials rubbing on each other. Just like when you scuff your socks on the carpet in the winter. You can separate charges because one material can take electrons from another. That's at the heart of how the Van de Graaff works. There's a complicated system of surfaces with various charges moving past each other, which induces charge separation. And ultimately, the top structure and the ball acquire a large excess of one charge. We're going to assume the Van de Graaff generators in this video acquire a positive charge, and we'll use that to introduce our new electrostatic concepts. The first demonstration is one of my favorite ones, though, and it's used to teach the idea that when you have charges in a conductor, they spread out as far away from each other as they can possibly get. And that's based on something you've known for a long time, that like charges repel each other. But the consequence is pretty important. If you have a charged conductor, the charges will be on the outside. So here's the demonstration of this. When I charge up this Van de Graaff ball, the charges are going to go all around the dome. I'm going to drop these conductive pie pans right on top of the dome. And I want you to watch what happens. Give it a little while to charge up. We can see here the running Van de Graaff generator with its positively charged dome. And one of the principles of charges in a conductor is that they will arrange themselves to get as far away from each other as possible. That's why I have them spread outside the surface of the dome. But when we put the pie plates on, now there's even farther away from each other they can get because some of the charge can move into the pie plates. Now this may seem a little bit weird, because you guys know that the positive charges are located in the nuclei of atoms. They can't move. The reason positive charges rearrange themselves in conductors, though, is that the electrons, the negatives, can move, and they're going to redistribute themselves to get the positive charge as far away from each other as it possibly can. So I think I have to show you what I mean by that. So if this is running and I throw these neutral pie pans on, in the top pie pan, an electron is going to go scooching all the way down and it will cancel out one of these positive charges. Now, of course, when that happens, it's going to leave the pie pan positive. And that's going to keep happening, and since the Van de Graaff is going to keep running, positive charge is going to continually be created, and positive charges are going to show up all over this outer pie plate. These parts here are also on the outside of the stack, and they're going to acquire a positive charge too. And since you guys know positives and other positives repel each other, that's going to put an upward force on the top pie plate. And the process is just going to repeat itself until every plate is gone. I'm standing right now on an insulating stool, and that means if I hold the Van de Graaff when it gets turned on, I should be brought to the same potential as it. I will have a charge all over me. It'll be the same charge on every part of my body, and that does interesting things to hair. I don't have the world's best hair for this. Mine's pretty thick and curly, but you should see something happen. Someone with thinner, longer hair can have a pretty amazing effect. So, I don't know if you could see my hair standing up and doing kind of wild things. When I discharge the Van de Graaff, you should see it drop. So obviously the Van de Graaff generator had an effect on things that were touching it. What I want to move to is how did it affect the rest of the room? How are things here affected, or here? Up till this point in physics, we've really learned about two things, forces and energy. And we have a way of describing how objects brought near the Van de Graaff could experience an electric force on them. We also have a way of describing that objects that are brought farther and farther away from the Van de Graaff or closer and closer, they're going to be changing potential energy. So we have a way of describing that too. The part of force that depends on where you are near the Van de Graaff, we call electric field. And the part of potential energy that depends on where you are, we call electric potential. Some people call it voltage. So what I want to do now is go through and explain a little bit of the math that helps you figure out the electric field and the electric potential. And to do that, we're going to start talking about a different force, gravity, which uses some of the same math, but we're a little more familiar with. After that, we'll briefly discuss electric field and electric potential, and then we'll do a couple more tricks with the Van de Graaff generator. So here's our two equations for the force of gravity. And I want to start with the older, more familiar one. The force of gravity equals your mass times 9.8, the acceleration of gravity. Have you ever considered that that means your weight depends on two very different things? One of them is a property of you, your mass. But the other is a property of where you are. Any object in your location also depends on that 9.8. So when we talk about how gravity is determined, the 9.8, or the gravitational field we'll call it now, that really represents what the Earth is doing to help create the force we know as your weight. The mass is what you're doing. So sometimes separating those two contributions, what you are from where you are, is helpful. And that's why we're going to define a concept called gravitational field. I've drawn this planet here, and I've drawn several masses around it. Notice that they're all at the same height above the Earth. Well, if we were going to go calculate how much gravitational force is on each of these, we would have to use Newton's law of gravity. And I've done the calculations for each color of the masses here. And you can't help but notice when you do it all in the same color that most of the equation is actually identical. Big G is the same in all of them. The mass of the planet is the same in all of them. The only thing that's really changing is the mass of each individual object. So we want to focus on the similarities between the objects here rather than the differences, because that could get us out of doing a lot of work. If we could look at the part of the equation that doesn't change, it gives us an idea about the environment the object's in, rather than the unique circumstances of that object. So we defined something called the gravitational field. We just took Newton's law of gravity. The gravitational field is the force of gravity divided by the mass of whatever object we're talking about. And that cancels one of the masses out of our equation. And we're just left with the gravitational field as G, mass of the planet, divided by r squared. On the surface of the Earth, using the radius of the Earth and the mass of Earth, this ends up being 9.8. We could draw something known as gravitational field lines that would help us keep track of the force of gravity at each location. I'm going to draw lines going into the Earth, evenly spaced around the Earth. And what this represents is how strong the force of gravity is at various distances from the Earth. We know it's stronger when you're close. We know it's weaker when you're farther away. And if you look at these lines, which are in the direction the force of gravity would be at every location, you can see that they're spreading out, just like gravity spreads out. So hopefully what you got out of that is that the little g we've been using all year is actually this whole chunk from the new Newton's law of universal gravitation. And it just represents everything that's about location. Your weight is your mass times all the stuff about where you are. Turns out that since Coulomb's law for the electric force is so much like Newton's law, we actually have the exact same situation. And this equation here, that might look totally new to you, is actually the same as Fg equals mg. We just replace mass with charge q. And just like we have a gravitational field to represent how mass alters space, we have an electric field to represent how charge alters space. Let's say on my Van de Graaff generator, I put a positive charge. Well, I've got a +2 here, a plus, a -3, a -2. These charges are all going to experience very different outcomes. Some are going to be attracted, some are going to be repelled. The strength of attraction and repulsion is going to be different. But the environment they're in is all the same. So it's important we keep track of the environmental effect versus the effect of individual charges. That's why the idea of gravitational field seems a little silly, but we really need it for electricity. The same location, which I represent its variables in yellow, can have a very different effect depending on your charge. We take the convention that the force on these charges, we draw the lines as if they were a positive charge. So the electric field we'd symbolize as this. And we can see that it too is spreading out as we move away from the Van de Graaff generator. Different charges brought near a charged object are going to experience very different electric forces. This one will be repelled because it's positive. This one will be attracted because it's negative. But the field is a description of the space. We can very easily convert from field to force by multiplying by our specific charge. I want to go off on this idea that the field describes the space around a charge. If you have a strong enough field near a charge and you bring other charges in, say on a grounded object, some really interesting things can happen. I'd like to show this with the Van de Graaff generator. What I'd like to show you today is that the distinction between insulators and conductors, it can really start to break down when we put ourselves in situations where there's very, very large charges. Air is usually a pretty good insulator. If you have bare wires running through the air, as long as no one touches them, electricity is probably not going to jump out of them. If the electric field gets large enough in a certain location, no insulator can actually overcome the energy that would be released if charge jumped, and insulators will start to break down. The wand is wired to the Van de Graaff generator. The Van de Graaff generator, its green base and the wand are wired to the earth through this pin, which we call the ground pin. And because the earth has a lot of electrons, when this ball gets too high a charge, it will start to steal them through the earth, either from its base or from this wand, and we'll see a lightning bolt. So when I have it relatively close, it makes lightning bolts fairly quickly, and they're not too big. The farther I go away, the less likely it is to happen, but when they happen, they're rather much. You can steal this from any nearby source of electrons, and we'll take the wand away. And it starts to take it from its own base, which is also wired to the earth. It's also perfectly capable of taking electrons from me. Ow. I don't know if you could see that bolt from my hand. It's not taking a huge amount of electrons, and that's why it's relatively safe for me to do.
Alright, so hopefully you could see that part of the calculation of force has to do with where you are. And it turns out that part of the calculation of potential energy has to do with where you are as well. This is a small mass, this is a big mass. If I lift them to a certain height, they each get a potential energy mgh. Of course that's different based on how big they are. But look at what part's not different. The GH part is the same for anything at the same height. So that part of the potential energy calculation just depends on where you are. If you wanted to know your specific potential energy, you'd have to multiply by your mass. The same thing would happen to a charge in an electric field. If I take a charge, let's say a positive charge that wants to be down here by a negative, and I move it up here towards a positive, that's doing work on it. That's going to give it potential energy. The mgh of electricity is QED, charge, electric field, and distance. And the ED part depends on where you are. So we call that part in this situation the electric potential, or the voltage. If you want to figure out how much potential energy any charge has at a given location, you just take the information about the charge and you multiply it by the information about the location, or the voltage.
So everything a certain distance from the Van de Graaff dome is going to have the same electric potential. Everything a farther distance is going to have the same electric potential. And they will have two different electric potentials between them. And regardless of how much charge there is in any location, that part of the energy calculation will be the same. So electric potential is just the potential energy divided by the specific charge's information. Notice that potential energy depends on two things, charge and voltage. So I said the Van de Graaff is at hundreds of thousands of volts, but I'm willing to let it shock me.
So here's that same equation. I apologize, I'm using U for potential energy. But potential energy equals charge times voltage, or potential. I'm sure you guys have heard about voltage before, and you know it has something to do with energy. The Van de Graaff dome was at 300,000 volts probably, relative to me. So that sounds really scary. But it's not voltage that hurts you, it's energy that hurts you. Because the Van de Graaff only transfers a small amount of charge, even with that huge voltage, very little energy goes into me, and I'm okay, mostly. Now, You probably know that we also talk about batteries and the electricity that comes out of our wall in terms of voltage. In the United States, 120 volts is what we have on our mains in the walls. Well, 120 volts could definitely kill you because an electric circuit has the ability to transfer much more charge. So even with the more modest voltage, we can get a lot more energy. We will be talking a lot about voltage in circuits, but we're kind of setting the stage with this video. Just like locations in space in this video have different potentials, different potential energies per charge, locations in a circuit can have different potential energies per charge. And we're going to see that that helps make charges move. We'll definitely talk more about that later. But for our last demonstration, let's take a look at how having different potential energies per charge across a light bulb can make it light.
I've got the Van de Graaff generator. It's going to generate its large positive charge on its dome. And that's going to create an electric field in this room. And what that means is charges at various distances from the dome are going to have different amounts of energy. And what's cool about that is a device like this simple fluorescent light bulb, much like the big ones we often see in the lighting in schools, or maybe you have one of these in your kitchen or your garage. This works by having a difference in energy across the ends of it. So believe it or not, I can actually light this just by holding it near the Van de Graaff. I'm going to do that. I'm also going to turn it 90 degrees, and we'll see if there's any difference.
So here's the reason why we might expect a difference based on how we hold the tube. We know that we have different potentials, different potential energy per charge when we're close than when we're far away. So in this situation, we have a potential difference across the tube. And that's what you would get when you hook it up in an electric circuit. In this case, I've got the ends pretty much at the same distance from the dome, so we don't expect a potential difference. So we don't expect it to light here. Let's see if that's what really happens.
Turn on the Van de Graaff. We'll go turn the lights out. All right, so I'm going to come in and hold the tube from the side. We'll see if we can get it to light up. So there you go. It is indeed lighted. I'm not touching the dome at all. It stays lit until I get it close to being in the vertical position. If I tilt it back, it lights up again. Here's one other fun thing I've noticed. I'm standing next to a metal chair, and watch what happens when I touch my foot to it. I bet you can hear that lightning bolt. That means there's charge passing through me to ground. That's making the bulb get brighter, as long as I do that. Kind of hurts though, so I'm going to stop.